Greetings. You're watching Team 11's report video for our information processing module project. For this project, we built an FPGA accelerated trading system that processes live market data and executes trades in under a microsecond, end-to-end. The system spans two pink Z1 boards and a cloud node connected over Ethernet. Let's walk through each board. Board A. Board A is responsible for turning raw market data into a clean order book that board B can trade on. Data enters as standard H5 messages sent from the laptop over UDP to ports 1, 2, 3, 4. This itch data is downloaded locally on the laptop. The ARM processor receives the UDP packets and passes the raw frame through DMA into the programmable logic. The first hardware stage is the itch parser. It strips the Ethernet, IP, and UDP headers, then decodes the 5 itch message types we support. Each decoded event carries an order reference, side, price, and quantity. The parsed event feeds into the order book module, the most complex block on board A. It maintains a full limit order book using a 4-way set associative L1 cache backed by L2 storage in DDR via the AXI HP port. The cache uses LRU replacement and write forwarding to avoid stalls. On each event, the order book updates the affected price level and computes an aggregate signed order flow metric. The order book pipeline takes 4 clock cycles per event. On an L1 hit, which is the common case, there is no additional penalty. The output of the order book feeds into the price level tracker, which maintains the top 3 bid and top 3 ask price levels. It uses a 5-state finite state machine with instant promotion when a level drains to 0. A background scan on VRAM port B discovers new price levels across up to 64 entries. This prevents L1 cache misses from directly stalling the pipeline. Board B.
Board B is where the actual trading decisions happen. It receives the 256-bit snapshot from the order book from board A over UDP. The ARM processor then pushes this through the DMA into the FPGA fabric. And from there, it goes through 3 hardware stages. The first stage is the feature engine, where the raw market data on its own, such as the bid price, bid ask, and order sizes, isn't enough to model on directly. So we need to derive signals from this. The feature engine computes 14 of these features over a rolling 16 event window. Things such as the 16-tick price return, how far the price is deviated from its EMA, the order flow imbalance, and so on. The pipeline is 82 cycles deep, where the hardest part was trying to get the timing close. The slope feature alone required 16 parallel multipliers, followed by a 3-level adder tree. And that chain carried over 10 nanoseconds, which was over our budget. So we split the reduction across 4 registered stages and got it down to 6.6 nanoseconds. 2 features also required division, and the divider core takes 69 cycles each. So rather than stalling, we run a BRAM conveyor belt in parallel, so it holds the early features and releases them exactly in sync with the divider output. So once we have the 14 features, the inference engine then combines them into a single score. It computes the dot product of the 14 features multiplied by the 14 trained weights in parallel across 14 DSP48 slices. These are summed into 2 register levels, where the biases are added, and the 32-bit score comes out in 3 clock cycles. The weights are then loaded via AXI GPIO at startup and can be swapped at runtime without touching the bitstream, which is what makes the server-to-node weight pushing work. The OMS, the order management system, is the final stage and consists of four pipeline stages. It takes a score and turns it into an actual trade, where the size is the absolute value of the score shifted to the right by 10 and clamped between 1 and 500 shares. So the higher score produces larger orders, and the direction of the sign where positive buys and negative sells. The OMS also tracks position, where it's capped at 2,000 shares long and no short selling. And there's a P&L kill switch in hardware that stops the trading in exactly one clock cycle if required.
For server-to-node communication, the cloud receiver can push a 40-byte UDP packet containing new weights, bias, and a PNL floor that can be pushed dynamically to the board B system.
We'll now do a live demonstration of our system. In order for our system to work, we must run 4 Python files. The first file we need to run is board C receiver pi. This will start our cloud-side logger. It listens on UDP port 5678 for the 24-byte trade records from board B. It loads the AWS credentials from an environment file using .env and uses Boto3 to upload to S3. Every 10 trades, it snapshots the CSV and uploads on a background thread so the receiver never blocks. It uploads the 2 locations in our S3 bucket, a latest folder that always has the most recent data, and a timestamp archive so we can have a full history of how our system has performed. I'll now run this script. The next files that we must start are the driver files. Board A must bind to a UDP port so that it can receive the itch data from the laptop. The driver then pushes the itch data into the FPGA through AXI-DMA. I'll now run this. Next, we must run board B's driver file. This will load the trained ML weights from NumPy files and then write them into the FPGA through AXI-GPIO registers. Then it will enter its main loop, receiving 256-bit market state vectors from board A via UDP. It will feed them into the FPGA through DMA, and it will produce 24-byte trade records, telling us whether it has decided to buy or sell. It will then send these via UDP to board C receiver pi so that the AWS can log its decision. I'll now run board B's driver. And finally, in order to send the itch data, we must use laptop itchsender.py. So once the overlays have loaded, I will send this and we will be able to see our system working. Okay, I will now send the itch data. And we can see A is working and B is making decisions. And now we will go over to see our AWS file once it has loaded, which we can see here, it has archived in the transactions folder. And now moving over to our secondary laptop. In the AWS section, if we reload the page, we get our latest file, we download it, and then we can view a log of all the trades made by our system. As we can see, the weights are updated and new weights are sent from AWS to our node. We also have a log of the decision made, the size of the trade, the score from the feature engine, and also the best bid and best ask.